let us try to understand this upsampling and downsampling in detail. Say, for example, it is a nearest neighbor, right? So as I told you, like there are many approaches that we can use to upsample the resolution of a feature map. But the pooling operations downsample the resolution by summarizing a local area with a single value, right? So let's try to understand. Say, for example, I have this one, right? So here I have 1, 2, 3, 4, right? In case if I do this nearest neighbor, so now the input is 2 cross 2, right? So the output is actually 4 cross 4, right? So the output is 4 cross 4. So what you can see here, 1, 1, 1, 1, and 2, 2, 3, 3, 3, 4, 4, 4, 4, right? So if you choose bed of nails approach, it could be the same input. It may give us the output. So if you use that bed of nails, and then what are we getting over here is like, so here we will get 1, this will be 2, this will be 3, this will be 4, and remaining all will be 0, right? Remaining all will be 0. I mean 0, it's 0, right? So 0, 0, 0. Clear with this now? Say, in case if you go with the option of maximum pooling, what we may get over here, like we will get it as, right. So in case if we, let me take a new whiteboard now. Okay. So now look at this, like in case if we choose maximum pooling approach, say for example, I have, so say for example, if I choose this one, there my drawings, okay, right? Second one. So let me explain this so that you'll be clear with all the concepts of upsampling and downsampling at least, right? So in case if I have numbers like say I have numbers like 1, 2, 6, 3. For example, if I have like this 2, 1, 1, 2, 7, 3, 2, 1, 4, 8. Say for example, if I use this max pooling approach, so what do we see over here? We will be looking into this, like which is the maximum, right? So out of this 1, 2, and 3, 5, which is the maximum? 5, right? So here 6, 3, 2, 1, which is the maximum? 6. 1, 2, 7, 3, which is the maximum? 7. 2, 1, 4, 8, which is the maximum? 8, right? So the rest of the network, what will happen now? So in case if we do, maximum unpooling, what will happen now? 1, 2, 3, 4. Say use positions from the pooling layer, right? So what I'm doing now, maximum unpooling, right? So what will happen now? Here it will become 0, 0, 0, right? 1. So here there is 2, right? So it is going to be like 2, 0, 0, 0, right? And then this is going to be like 0, 0, 3, 0, something like this, right? So 0, 0, 0, 4, right? So from input 2 cross 2, we are getting it to 4 cross 4, right? So like this thing you have to understand about like upsampling or downsampling, how is it being performed, right? So transpose convolutions are by far the most popular approach. They used to develop a learned upsampling, right? So what they do is like they take 2 cross 2, they take 2 cross 2 input, right? And then they use 3x3 transpose convolution, 3x3 transpose convolution, right, with a stride 2 and pad 1, right, stride 2 and pad 1. And then, so let me show you like how it works basically, right? Say for example, this is the input, right? So 2x2, this is the input. So now what will happen? This input gives weight for filter, right? This input gives weight for filter. Now see, they see that right? So here, light. Look into this one. So what will happen now? Say for example, so what will happen now when you say stride 2 and pad 1? This is how it will work, right? So from here to here, right? Not this one, right? So when you do stride 2, 3x3 transpose convolution stride 2 and pad 1, so this is what will happen now. Now this one, hope it is clear, right? So what is happening here? Here it gives the somewhere output overlaps. So the filter moves 2 pixels in the output for every 1 pixel in the input. So the stride gives us the ratio between the movement in output and the input, right? So when you talk about typical convolution operation, it will take the dot product of the values currently in the filter's view, and it produces a single value for the corresponding output position. Transpose convolution does the opposite. So in a transpose convolution, we take a single value from the low resolution feature map, multiply all of the weights in our filter by this value, projecting those weighted values into the output of the feature maps. So what we do over here, say for example, I have an input, say A and B, and I have filters like X, Y, Z, right? So what will be the output now? Like the output is going to be AX, AY, and AZ, right? AX, AY, and AZ. Similarly, I will get it like BX, BY, and BZ, right? So what's happening here? This is basically, right? So let me show it very clear, right? So let me make it very clear to you. So here this will get added also, right? So that also we have to mention over here. Say, I hope this is clear. Just I'm showing like how it works, right? So what's happening here? Like in convolution operation, like we take the dot product of the values in the filter, and we produce a single value for the corresponding output position. And a transpose convolution, just the opposite. What it does is it take a single value from the low resolution feature map and multiply all the weights in the filter by this value, and it projects those weighted values to the output. So for filter sizes which produce an overlap in the output feature map, say 3x3 filter with a stride 2, the overlapping values are simply added together. So here this tends to produce a checkerboard artifact in the output, and it is actually not desirable. So it is always best to ensure that your filter size does not produce an overlap, right? So that we have to be very much careful with, right? So like here we use convolutional networks are being used. The approach fully convolutional network is actually trained end to end, pixels to pixels, for the task of image segmentation. We have seen that it was introduced by Long et al. And they proposed that adapting existing well-studied image classification networks like AlexNet to serve as the encoder module of the network, appending a decoder module with the transpose convolutional layers to upsample the coarse feature maps into a full resolution segmentation map, right? However, the encoder module reduces the resolution of the input by a factor of 32. The decoder module struggles to produce fine-grained segmentation. So the semantic segmentation faces an inherent tension between semantics and location. And global information resolves what? Well, local information resolves where combining fine layers and coarse layers lets a model make local predictions that respect global structures, right? So the skip connections are being added. So the authors address this tension by slowly upsampling the encoded representation, adding skip connections from earlier layers and summing those to feature maps. So these skip connections from earlier networks, say for example, we have an input, right? And then we have pool 1, pool 2, pool 3, pool 4, pool 5, right? So from this, what you can see is, right? So this, right. So now this pool 4, see this pool 4 is doing some prediction, right? Pool 4 prediction. Similarly, like you can see that here there is two crops upsampled prediction, right? Upsampled prediction. Clear? So here there is 2 cross upsampled prediction. So what will happen? This is from pool 5, right? And this is pool 4 prediction. And now these two are summed up, right? And it again leads to 2 cross unsampled prediction, right? And then from here we get again pool 3 prediction, right? So there is pool 3 prediction. Now these two will be summed up and it will lead to 8 cross upsampled, right? Upsampled prediction for FCN 8. Clear? Right? So what is upsampling over here? So this stage is upsampling, and similarly this stage is upsampling. So here we are getting output as 8 upsampled prediction FCNs, right? So here there are skip connections from the earlier layers in the network, like before this downsampling operation. It should provide the necessary details to reconstruct accurate shapes for segmentation boundaries. So we can also require fine-grained detail with the addition of these skip connections, right? So fully convolutional architecture primarily expands the capacity of the decoder module of the network. So more concretely, they propose UNet architecture, which consists of a contracting path to capture context and a symmetric expanding path that enables precise localization, right? So this simpler architecture has grown to a very popular and adopted for a variety of segmentation process, right? So you can see this UNet, right? So here the original architecture introduces a decrease in resolution because of the valid padding. So some practitioners opt to use same padding where the padding values are obtained by image reflection at the border. But Long et al., like in the FCN paper, they reported that the data augmentation did not result in a noticeable improvement in performance. Ronneberger et al. Said that it's a key concept for learning, and it appears as if the usefulness and data augmentation depends on the problem domain. So now let us have an overview on UNet variant. So the standard UNet model consists of a series of convolution operations for each block in the architecture. So there will be more advanced blocks that can be substituted in for stacked convolution layers. And they swap out the basic stacked convolution blocks in favor of residual blocks. So this residual block introduces short skip connections alongside the existing long skip connections found in the standard UNet structure. So they report that the short skip connections allow for faster convergence when training, and it allows for deeper models to be trained. So they propose the use of dense blocks, and then still it follows UNet structure, or giving that the characteristics of denseness make them a good fit for semantic segmentations, as they naturally induce skip connections and multi-scale supervision. So the dense blocks are useful as they carry low-level features from previous layers, and it directly alongside higher level features from more recent layers, allowing for highly efficient feature reuse. So one important aspect of this architecture is the fact that the upsampling path does not have a skip connection between input and output of a dense block. The authors note that because the upsampling path increases the feature map spatial resolution, the linear growth in the number of features would be too memory or demanding. So only the output of a dense block is passed along in the decoder module. Right. So UNet is a network whose training strategy relies on heavy use of data augmentation in order to use the annotated images efficiently. So the architecture is made up of a path that captures context and symmetric expanding path, which is to enable precise localization. So in this architecture, a fully connected convolution layer is modified to work on a few training images, yet yielding more accurate precision. So this is very important because the architecture was initially proposed for medical image processing, where a lots of training data is scarce. So this applies elastic transformation in order to achieve augmentation. So you can look over here, like there is convolution 3x3 ReLU, copy and crop, maximum, pool 2x2, app convolution 2x2, and convolution 1x1, right? Okay, so the benefit of downsampling a feature map is that it broadens the receptive field with respect to the input for the following filter given a constant filter size. So this is more desirable than increasing the filter size due to the parameter inefficiency of large filters. So what do the dilated convolutions do? It provide alternative approach towards gaining a wide field for of view while preserving the full spatial dimension. Right. So some architectures swap out the last few pooling layers for dilated convolutions with successively higher dilation rate to maintain the same field of view while preventing loss of spatial detail. Right. So here again, like if we have to define a loss function for this image segmentation, that is basically pixel wise cross entropy loss. So this examines each pixel individually. It compares the class predictions to our one hot encoded target vector, and it evaluates the class predictions for each pixel vector individually, and then it averages over all pixels, right? So we are essentially asserting equal learning to each pixel in the image. So sometimes this could become a problem if you have unbalanced representation in the image, because the training can be dominated by most prevalent class, right? So like uh, we this last weighting scheme helped UNet model segment cells in biomedical images in a discontinuous fashion, such that the individual cells may be easily identified within binary segmentation map. So a loss weighting scheme for each pixel is such that there is a higher weight at the border of the segmented object. So there is another one popular loss function for image segmentation, that is dice coefficient, which is essentially a measure of overlap between two samples. This could be ranging from 0 to 1. Where dice coefficient of 1 means it is perfect and completely overlap. The dice coefficient was originally developed for binary data, and it can be calculated as dice is equal to, right? So what is this A intersection B? That represents the common elements between A and B, and A represents the number of elements in set A, and B represents the number of elements in set B. So to evaluate dice coefficient on segmentation task, we can find out A intersection B, the element-wise multiplication between prediction and target mask, and then we can sum the resulting matrix. So our target mask is binary, so we effectively zero out any pixel from our prediction which are not activated in the target mask. So for the remaining pixels, we are penalizing low confidence predictions, higher value for this expression, right? So if we have to quantify A and B, some researchers use simple sum, whereas other researchers use squared sum for the calculation. So like again, it depends upon the scientist, like which approach is better that can be taken. So in case if you think that why there is a number 2 in the numerator, in calculating dice coefficient, because our denominator is double count the common elements between two sets. So in order to formulate a loss function which can be minimized, we will simply use one dice, right? So this is called as soft dice loss, because we directly use the predicted probabilities instead of thresholding and converting them into a binary mask. So with respect to a neural network output, the numerator is concerned with the common activations between our prediction and target mask. So the denominator is concerned with the quantity of activations in each mask separately. So this has the effect of normalizing our loss according to the size of the target mask. So the soft dice loss does not struggle learning from classes with a lesser spatial representation in an image. So a soft dice loss is calculated for each class separately and then average to get a final score, right? Oh, so this is the understanding, or this is the idea you should get to understand the segmentation, semantic segmentation process. So I think this is clear to you,